Welcome to this latest video on the Interlock system. Now this is a model railway Signalbox interlocking system, but from version 0.5 onwards it's now got block signaling automation added. So let's have a look at what is going on. So in the original version, the idea was to build an interlocking system that would prevent you from setting signals or points, turnouts in the wrong direction. So the idea is, if we have this piece of track here, if we have this signal here that is set to green, the interlock system has to make sure that signal 1 coming in the opposite direction is not set to green as well, because obviously that is going to cause a collision. In the same way, we need to make sure that this signal 2 cannot be operated if the track is going, in my case, to direction 0, because otherwise I'm going to get a derailment. So the original version allowed you to create sets of rules, making whatever track plan you wanted, and the system would check that your interlocking was working correctly. Now there is a trainee mode and a full interlock mode. Full interlock mode means nothing will move unless you get it right, whereas the trainee mode will allow you to do things and make mistakes and just beep at you annoyingly. Now for the latest version, block signaling has been added, and I'm very thankful to some people on a Facebook group who gave me lots of information about block signaling, because I'm not a signaling expert. Anyway, what is block signaling? Well, if you go out onto a modern railway system, this is going to be based on the UK signaling practice, but you can change the signaling to whatever version you want. So in the UK, you would have a system. I'm going to be using 4 aspect signals as my example. And as the train moves along this line of signals, here is my virtual train. Train A is just approaching a green signal, which means because this block of track is now occupied, the signal behind it goes to red. The signal on the block before that goes to a single yellow. The block before that with 4 aspect signals goes to a double yellow. And then, of course, the signal before that will then automatically go to green. And then we've got train B arriving, and obviously it has come to signal 6, which is green. So if train B started to catch up with train A, he would start to see increasing warnings until, obviously, if he got too close, he's going to see a red and he's going to have to stop. Now, what I've done within the interlock system now is I have built in a simple way of building block signaling control that will do everything in an automated format for you. Now, as always, below the video there is the link to the Interlock page on the Digital Town site, and that will take you over to the resource page that has not just the code and the circuit diagrams for download, but also all of the instructions on how to use the system. So going over to the Digital Town site, this is the page that you'll come across. There is the video for today's lesson, and also if you click on this link below, you will get the circuit diagram and the code for the demonstration version that I'm going to show you today. You can just click on the download the sketch. That will take you to the latest version. I've left the original version available so that people who want to use that sort of simpler version can use it, but today I'm going to be concentrating on the version 0.5, and that format will continue in future versions. Now, going back to the signaling diagram here, today's example is going to have a signal box section where we're going to mimic just this little part of the signal box. I'm also going to mimic signals 6 to 10 and show you a block signaling version. So let's have a look at the breadboard, and you can see today's bird's nest of wiring. So this is today's breadboard, and at first glance it looks extremely complicated. Actually, when you look at the circuit diagram, it's pretty simple. We've got the Mega 2560. This will handle up to 100 items, so that would be signals, turnouts, points, crossings, blocks, whatever you want. It'll handle 100 items. Now when we come to signals, this is a 4-aspect signal. That counts as one item. It doesn't matter how many aspects the signal has. The system will handle up to 5 aspects for those modeling the latest high-speed lines in the UK. So you can have 100 items, 1,000 rules, and 100 signal monitors. That should be enough for most people, but if you use the ESP32, I had 400 items, 4,000 rules, and 400 signal monitors, and I'll be honest, I gave up after that because that was enough. There was still memory to spare, so you'd get more on there if you want. So if you've got a really big system, the ESP32 is the way to go. So looking around the breadboard, we have the 1602A I2C backplaque liquid crystal display. The latest version can use any display, so I've just put this in because I already had it out of the workbox, so I just thought I'd add it into the new system. I'm using my piezo speaker just as an audible warning that something has gone wrong. For my turnouts and points, I'm using double press buttons. You may notice as the servo moves, you can see that the display is fading in and out. That is because it's drawing too much power. My desktop supply just isn't big enough for this. You suddenly start to use up an awful lot of power. I've then got the buttons for the signals. Now, if I press signal 1, as you can see, that's success. It goes green. If I press signal 2, I get an alert. Now at the moment that signal has worked, but I've got the error message to say that the error is that the point is set to direction 0, which in my case is going towards this signal 1. Obviously there would be a second error if I cleared that, but we'll now put it into full interlock mode. So I'm going to turn signal 2 off. Now if I press the button, I get the alarm, but you'll notice the LED doesn't change this time. So full interlock mode stops something actually working, whereas the trainee mode will sound an alarm, but will allow you to still continue. The reason for trainee mode is if you've got a layout and you just want to move some stock from one end to the other, if you've got to set all the signals every time you want to move a turnout, it might just drive you mad. So you can turn it into trainee mode and just move things around just with the annoying beep. Down in the bottom left hand corner, I've got my block signaling. Now, as I've said, I'm using 4-aspect UK. So that goes green. We then go to double yellow, single yellow, and red. Now, if we imagine our train is moving along the board, as it goes through the first signal, you see that that signal then goes to red. As it goes into the next block, obviously the next signal goes red, and as the back of the train clears the first block, that signal will go to yellow. Now, as we then come to the next block, again, it goes red. As the back of the train clears, this signal now goes to yellow, but this one now goes to double yellow. As we now move up to this next signal, this one's gone red. The back of the train has now cleared, and we can see that we now get a yellow, double yellow, and green. This one is single yellow because it's not actually monitoring any other signals further up the line. You can add virtual signals into the new system to allow for it to actually be monitoring signals that don't actually exist in reality. So that is how the block signaling works. And if I had a second train that had come up into this other block. As you can see, I get a red signal if because this train is now in the block, but this driver would now be approaching a single yellow, and after that he's going to have a red because the next block obviously is occupied. Now, one thing to be aware of that I didn't do on the board here is that these signals here that have Signalbox interlocking rules can also be signals within a block system. So the rules that are applying to these can then be applied on top of the rules for these individual signals here. So it makes a pretty comprehensive system, and it allows you to set whole routes if you require. So going back to the website, how do you get started? Well, I've put a link here for instructions for version 5 or greater. There are two sets of instructions. One is the main sketch overview, and the other are input functions. Now, your input functions are how you input rules into the system, how you send commands to the system, all of that sort of stuff. Whereas there are then some output items that are methods for getting, if you like, information out of the system. So let's work through the whole thing. Let's go down to the main sketch overview. And in fact, before I start, let's just bring up the sketch itself. So here we have the sketch, and the first thing that you'll notice is that there are a number of tabs. And what I've done then is given some information about each of the different tabs. Now, the first tab obviously is that screen that you see when you first start, and it has a few definitions in it. The important part is that you've got to include the class. This is a bit like including a library. The reason I've rewritten it like this is it will allow you, when you are adding your own code, to have less chance of interfering with the interlock information. So by setting this as a class, if you like, the variables that I'm using are hidden within the class, so you're not likely to accidentally ruin something in the system. In the setup, I start off with my serial begin, and this prints out the file details to the serial monitor. The next command that you need is the my Signalbox initiation. This just sets up the system. Now, going back to the website, if you look through the information here, there are some informations about the definitions, the setup, and then finally coming down to the main loop. If I go back to the sketch, the main thing that is in the main loop, he says scrolling down, is that you've got to have this line of code, and this is constantly running in the main loop, checking all the interlock code. Now obviously you can add your own code into the loop, and you'll see that in the demo version that I'm going to show you in a bit. The important thing though that you need to note, and it is written here in red, is do not use the delay function within the loop or in any of your code when you're working with something like this, because if you use delay, you will mess up the timings of the system and you will have all sorts of problems. So on tab 1, the items that you must have, if you like, are the run the interlock system. We've then got the interlock init, and further up we've got including the actual class system. And just like a library, I call mine my Signalbox, which means every time I use a function within the interlock system, it must be prefixed by my Signalbox. Now the rest of these items are how we now load inputs and signals. I'll come back to those, and also monitors, and then I've added some commands. But going back to the first screen, I just want to run through the items that are listed here. There are some definitions. A point has a value of 1. For those of you in the States, I've also added turnout as a separate thing. Why bother trying to rename stuff? We'll just leave them as separate names. The system doesn't care. A block, a crossing, and then I've got other 1, 2, and 3. And you can change the names for those in the system. Those were for items that I didn't know what they were. So if you've got something really weird, then you can add that into the system without a problem. The other definitions here is obviously I've got a point, and my definition for, in my case, on my layout, I use left is 0, right is 1. I know various other systems, they have, I think it's, if you're going straight down the main line, you have one value. If you're turning off the main line, you have the other. Set your definition name to whatever suits you. It doesn't make any difference. I've built one for turnouts, the points. The important thing is that you have one that is a 0 and one that is one definition that is a 1. Now, when it comes to signals, once again, there is only 2 definitions, 0 or 1. 0 means red, stop, danger. 1 means clear the signal, go, green, yellow, double yellow. The system will take care of the color of the signal. All it needs you to do is say, is this ready to go, rather than a 0, which is a stop. Again, crossing, if the crossing gates are closed, there's traffic going across, you send a 0 because it's a stop. If you've opened the gates, then once again, it will get a value of 1. And then again, with the others, 0 and 1, you can rename that to whatever you want. Now, going back to the sketch, the next tab is the custom functions. And these are a set of functions that receive information from the Interlock system. Now, going back to the website, this is the custom functions, and once again there is a whole load of information in here just so that you've got that data there. You don't have to keep rewinding the video, but I'm just going to quickly whiz through how the different functions work. So the first function is your mode state. Now, on the demo that I've got on the desktop, I've got, if you like, an alert that's going, and I'm sending information to that LCD screen. In the latest version, that is not required. In fact, you can run this on just an ESP32 or a Mega without anything attached, just the bare board, and you can get this little demo running on there. So what I've done, just to show what's going on, is this function, when the mode gets changed within the system, this function gets called, and you then decide what you want to do. Now, in, if you like, the sketch as it comes, if you like, by default, I've got this so that it is just going to serial print to the serial monitor. If I now bring up my workbench version, now in my workbench version, when this is called, you'll notice that it sets the LCD cursor, it writes to the top line, Interlock ++ mode, and then depending on the mode state, it then sends information either to say it's in full interlock mode or training mode. So although the, if you like, the basic version just comes with serial prints in there, you can then add in whatever code you want. I've done this to make it as flexible as possible. Going down, the next item we have is the error tone. Again, I've tried to make it as flexible as possible. This serial prints out an error tone, whereas in my demo, I've left the serial print in, but it actually has a pin, buzzer pin, and it sets a tone. It plays for, was it 2000 Hertz, and it plays for ½ a second. So again, that would show you in the demo that I'll give you how to set up an actual tone. It also means, of course, if you comment out that tone, that it all becomes silent and you can just see the error on screen. Now, this is the part of the system that sends the commands to your layout. So you've pressed some buttons, you've asked Interlock to do something and to check some rules. This is when it then says, okay, you've passed the interlock rule, or you're in trainee mode and you want it to do it anyway. This sends out the information that you need to be able to build your control system. So at the moment, if the basic version, it just gives a serial print that some data has been received. The item ID of the item that is receiving an instruction and its actual instruction. Now, I've put a switch statement in here in the version that I've built. As you can see, I'm using PCA 9685 boards for the LEDs. The reason for doing that is each board can control 16 LEDs, and I can alter the brightness. At the moment, I'm using 4095, which is maximum brightness, and 4096, which means it's fully off. But if you found that the signals were too bright, you could change this value down to 3000, and that would make the signal slightly less bright. So again, it allows me a little bit of the ability to customize the signal brightness without having to mess around with lots of different resistors. Let's just put that one back. So basically, I have written a switch statement. Now, on my breadboard, if we just go back to it, the code we're looking at is for signal 1, and signal 1 is either green or red. It's a 2-aspect signal. So in my demo code, I am turning one LED off and turning the green LED on if I receive a value that's greater than 0. If my instruction is a 0, then I turn the red signal on and I turn the green off. And that's the same for the first signals up to signal 5. Obviously, signal 4 is not a signal. In my case, it's a servo. So again, if I get an instruction of 1, I'm going to move the servo to 30 degrees. Signal instruction of 0, it's going to go to 90 degrees. Now, on a full layout, I would probably have these on yet another PCA 9685 board, just because it's just easier. You can have far more servos. So that's the instructions, if you like, for 2-aspect and for turnouts or points. We then come down to signal 6, which is a 4-aspect signal. So signal 6 will receive an instruction of a value between 0 and 3, depending on the monitor and how it's running. So if I get an instruction value of 0, then I turn on my red LED and I turn off yellow, green, and the top yellow. If I get a value of 1, then it's red off, 1 yellow on, green off, top yellow off, 2 double yellow, so it's yellow on and yellow off, while the other 2 are, yellow on and yellow on, red and green are off, and then finally, if it's a green, I turn everything else off except for the green that is fully on. If I was using 5-aspect signals, there would be a case 4, and I would actually have to set up some code to flash the green, which I believe is how these 5-aspect signals work. So you can see that for the signals 7, 8, 9, and 10, I've just repeated this code over and over. So we're in a switch statement, which is doing the case of the signal or the turnout, Then within that, I've done a separate switch statement instead of an if statement. And the switch statement allows me to control multiple LEDs at the same time. Again, the idea is to leave this as open as possible so that you can do this however you feel is right for your layout. One of the things I've really aimed at is keeping the system as open as possible. So these switch statements here, if you were using DCC-EX, very easy to set this up as a serial command going to DCC-EX that would move your turnouts and could then create your own DCC accessory decoder commands. You can do it, I know how to do that for the NCE power cab, and the same with the now rail system. So the idea was to leave this as open as possible. Obviously the demo shows servos. This could be connected to some MOSFETs and you might be firing solenoids or sending instructions to tortoise motors. The choice is up to you. Now moving down this page, the next thing is we've got this function int check results, and this passes the results of a interlock test. So what we've done is we've sent a command to say that we want to move point or turnout 4, and the interlock system has checked it against the rules. Now what it does is it sends out the interlock state, which is 0 for success and 1 for a failure. It gives the item ID, the instruction that was sent, and it passes a string which is the name of the item. At the same time, if you get a success, then the check item ID, the check instruction, and the check item name will either be zeros and the name will be blank. Now, if your rule fails, then you will get the item ID, the instruction that is causing the interlock to fail, and again, the name of the item. Now, the reason for that is if I go back to my demo code, I scroll down to this, all I'm doing here is I'm creating a string and it's sending that to the top line. So that's giving these items, it's passing these to the top line. If I have a failure, if I've got an error, I'm creating a string of the items that were checked and has failed. If not, it passes a string that says success. So those are the, if you like, the custom functions, the output functions that Interlock has. So very few items there to learn. And again, you could just have this serial printing to the monitor if you don't want to add a screen. At the same time, you could use a variety of screens, and of course you could even log this information if you want at the end of the session to show which operator made the most mistakes. That's up to you. You can use the output as you wish. Now, going back to the tabs at the top, the next one is called interlock.cpp, and the good news is you don't need to touch that. This is the interlock code. It's, if you like, part of that class, that library system. You don't need to touch that at all. Now the next tab along is interlock.h. Now again, this is part of the interlock system. Going back to the website, there is one set of circumstances that you may wish to change something on that. And that is to do with the names. Now, I used signal point, turnout, block, crossing, other two, other three. If you've come up with something and you want to give this a more descriptive name, then all you do is go into the system, find that line, and just change that to your new name. The only thing that you need to be aware of is that the name cannot be longer than 8 characters. And obviously you can't add new names, but yeah, just keep it to 8 characters and you'll be fine. If you go over 8 characters, you will cause some problems. But that is the only change that you would ever need to make on the interlock H page. So for most people, interlock.cpp and interlock.h will never be used. Next tab is the interlock setup.h. And this is just where you can set some default values for the system. So you can do your default startup mode. I've got it defaulting to 0. Obviously, if I change that to 1 when the system starts off, it will be in full interlock mode. We then have the interlock processing speed. This is the delay between processing multiple items. So if you fired a batch of instructions at the system, it will process them one after another, and this is the gap between them. Now I have set this to 10 milliseconds. That is a very short period of time. You could move it down to 1 and it'll be fine. It's almost instantaneous. There may be some odd times when you might want to increase this value. So if you think about trying to simulate a manual signal box, imagine the poor signalman is going to move a lever, then he's going to move down the signal box, and he's going to move the next lever. There's going to be a few seconds between each movement. So you might want to increase that value to 2000 or even 3000 if you want to simulate that time gap. I have done it and it's a bit of a fun on the breadboard and could be interesting on a layout. However, there are some issues because obviously everything looks like it's working in slow motion, which it actually is. Next, we come down to these values here: int num inputs, int num interlock rules, and int monitor block signals. Now, I've got these set as 100, 1000, and 80. These are about the maximum that a Mega 2560 can run. If you are using less items, and most people will, I would advise you to reduce this number. So if you've only got 30 items, move this down to 31, 32, or even to 30. Again, very few people are going to have 1,000 rules, so reduce this down to a value that is much closer to the number of rules you have. And again, the same for the monitor blocks. The monitor blocks are the number of signals that are in the block system. Obviously, you can increase these, but the issues with increasing the values is it uses more and more memory. So these, if you like, are the maximum values for the Mega 2560. If you're using an ESP32, you can set this to 400, 400, and 4000, and the ESP32 doesn't even seem to blink at it. You know, it's got so much more memory. So that is sort of one set of settings that you may wish to tweak, especially if you're loading a lot of your own code. Then you're going to need some memory space, so reduce these values. Just bringing up my demo version, you can see that the breadboard version, I left the inputs at 100. I dropped the number of rules down to 300. I'm nowhere near that, but just dropping that, you can see that the memory usage dropped to 52%. If you are running the bigger version, you can see that I'm using 87%. So quite easy to run out of memory if you've got too many of these rules or inputs or monitors. One thing I would say about this, when you upload the code to your board, if you see this getting towards the 90%, if you start to go over 90%, you need to start thinking about reducing these drastically. Otherwise, you will have some interesting issues, especially with strings. if you're using normal strings rather than C strings. Now, scrolling down to the bottom of the setup, there are two definitions here. One I've got commented out, one I've left comment open. These are diagnostics. Now, you would normally comment these out when you finish the code and got everything running, but these will put data up onto your serial monitor, even though it's in the custom functions as well. But sometimes there is some extra information that will help you in your diagnostics. The signal monitor diagnostics, this is for the block signaling. If you are not doing diagnostics, make sure this is commented out. The reason is that the diagnostics introduces a delay into the system. Now, the reason is, if I load up the other sketch, when my system starts, my demo system starts, it sets signals 6, 7, 8, 9, and 10 to clear, to basically, you can go. What happens then, as soon as you do that, the interlock system, the monitor system, will start looking to see what is the maximum clear that the signal can be sent to. By that I mean, should the signal be red, yellow, double yellow, or green? So it will check the signal in front to see the state of that. Now, that happens so quickly when I start the system that by uncommenting this, you can actually see the data on the serial monitor, and you can see that your signals are processing the information in the right order. But because of that delay, make sure that this is commented out when you are actually putting it onto any kind of layout. So for most people, when it comes to the setup page, you're just going to reduce the number of inputs to roughly what you've got, reduce your number of rules to what you need, and reduce your monitors to what you need. Now, if you set these values too low, don't panic, because the system will warn you if you put too many items in. And those warnings are listed here in the user guide. So to make sure I saved as much memory as possible, the system puts out error codes to the serial monitor if you make a mistake. And the error code, so there will be a value for the error code. So you can see codes 2 through to 12. It will give you the function that the error has occurred in, and then it will tell you what the item is that has caused the problem. It covers just about everything. So if you get an error message when you start the system, and again, you will get an error message that the system has failed to initialize, and it will give you the list of errors above. So when you start putting rules in, if you've done something wrong, the system's actually going to tell you, come to the user guide and you can work out what the error is. So as I've said before, the setup page, a couple of mods to be made. The main screen you will use is the interlock page to set up your information, and then the outputs will come through the custom functions. Now, what we're going to look at now is how you actually input data into the system. Now, in the old system, you used to put this in an array. What I've done is written some custom functions to make all this easier. And as I've said, it checks for errors and gives you an error message if you get it wrong. So going back to the Digital Town site, if I just scroll back up to the top, the bit we now need to look at is the input functions. And you have a list here of all the different functions and how they work. Some of these functions are to do with loading. So we've got loading inputs, loading signals, loading rules, and loading signal monitors. Those are the, if you like, the main items that you're going to put into the system. There are then some other functions, list input types. So if you put this at the end of the setup, when the setup finishes, it will list all the input types that your system has. You can do the same with the inputs. So that would give you, as you've added inputs into the system, you can list them to make sure they are all exactly as you wanted. Again, same with rules, same with monitors. Those are the main things. Yeah, let's have a look at these and now work through the difficult bits. So the first thing is loading inputs. Now, when you're loading an input, this is any item, so a block, a crossing, a point, turnout, and other, anything that is not a signal. Signals are loaded in a different way, but this loads our input type. Now you've got your definitions. I've got them obviously on the sketch, but I've put them in here just as a reminder. And the way these are loaded is quite simple. You use this function, mySignalbox.loadInput. 4 is the unique number for that item. Now, signals, points, crossings all must have a unique number. And then I've put in the definition point. Obviously, if you're in the States, you're going to put turnout in. 12, item 12, let's imagine we have a crossing. That again is how the information will be added. Now, you can, instead of using the word point, you could just use the definition value, which is a 1. So this line can be written this way as you become more experienced. And again, crossing, if you look on the list, is a 4. So I've just put a 4 in here. Now, going back to the sketch, you can see that I've put a couple of examples into the setup. All of this information just goes into the setup, one line after another, but it must be put in after this, basically your serial begin and your initiation of the system. If you try to put this in before the system has started, obviously it's not going to work. Right, the next thing we're going to do is look at how we load signals. As you can see, it's a pretty simple system. The function, going back to the explanation, is the item ID of the signal and the number of aspects. So coming back to the code, you can see that signal 1 in my case is just a red and green. So signal 1 is its ID, 2 is the number of aspects, and I've got the same for 2, 3 and 5. And then you can see that I went from 6 to 11 and I set those up in my little demo as 4 aspect signals. Again, you can change that to 5 if you're using 5 aspect signals. The important thing to be aware of course, is this is only for signals, just as these are only for non-signal inputs. Now, the next item in the list is the rules. Now, the rules, we use the function load rule, and again, I've put some examples in here. So we have the item ID of the item that we wish to move or change its state. So that could be the signal or turnout or a crossing, and the status that we want it to go to. So for this one, I have got that turnout for me is number 4, and I want to set it to a direction to the right, and the rule that it's checking for is signal 1 should be set to sig st, which that definition is a 0, which means stop. So that signal should be stopped. Again, signal 2 should be stopped. That it can be written. I've done one for signal 3 here, writing it without the definitions. So it's a 4. 1 for me is right. 3 is the item that's going to be checked, and its state should be 0. So you just add in your rules in that way, very similar, in fact identical to the old system, except you don't have to put it into an array, you can just put it into the function. Now the advantage of putting these into the function, where are we, where's my rules, here's all my rules that I've loaded. You can see for the demo that I've set up, we have a number of rules. This is, if you like, the basic sketch. On my full system, very, very similar, because obviously I've only got a limited number of turnouts. I've also put in the signal monitor rules. So the signal monitor rules are very, very simple to add. You have two variables that you pass across, the ID of your signal and then the ID of the signal that it is watching. If you like, that would be the next signal up the line. So if we look at our diagram, wherever it has gone, hang on, let's just scroll up there. You put in the item 6 is monitoring signal 7 if we're going in this direction. Obviously, if you're going in the other direction, 7 would be monitoring 6. So as you can see in my demo, 5 monitors 6, 6 monitors 7, 7 monitors 8, 8, 9, 9, 10, and 10, 11. One of the things just to be aware of, these do not have to be in numeric order. You could have 8 is monitoring 11. There's no need to have these sort of starting at 1 and moving up. If you've got your signals in a certain area, in a certain range of numbers, not a problem at all. The same with the items. So coming back to our user functions, one of the other functions that we have is the set mode state. Now basically this line will set it to trainee mode and this line will set it to full interlock mode. You could have this triggered by your own button, which is exactly what I've done in my demo version. So in the setup, I've just put an example of how you would set the mode state. This would normally be called by a button, which is exactly what I've done in the breadboard version. Finally, we've got the function check interlock rules, which is the one that you would call when an item wants to move. So this would be a function that is called by your button or some command that is saying set a signal or move a turnout, operate the crossing, and all you do is you send across the item ID number and the state that you want it to move to. So we've got some examples here. Again, this is my turnout or point number 4, and the command I want it to move left. Now then I've got another one here. This is turnout number 414, and I want it to move right. Again here, signal 7, and I want to set it to clear, to go. Again, you can write them without the definitions if you wish. The same things are down below. So these are the things that would be called by your buttons, your different inputs to make the system work. Now going back to the sketch, I've put some examples. Now I've put these in the setup as a batch just to sort of show how the system works. It's going to set signals 5 through to 11. You'll notice that it says here that signal 5 is going to cause an error because in the setup that we have here, that's going to conflict with signal 3. I've then put in signals 6 to 11, which are the signals that I'm using for block signaling, because as I set these to clear, to go, then you can actually put in the monitor. If you go to that setup, if you uncomment the signal monitor diagnostics, you can actually watch the system how it actually updates those signals bit by bit. You'll see there different values changing through sort of 1, 2, 3 as they increase in, if you like, their clear state, going sort of amber, yellow, double yellow, and green. So that's the basics of how the interlock sketch works. Of course, the bit that we haven't shown is how we're going to add buttons and, in this case, block detectors. So let's have a look at how that would work. So going back to the introduction, you will see the code and circuit diagram, and you can just click on this to download it. It'll come down as a zip file, and you will finish up with this circuit diagram. Now, I have put toggle switches in here. The reason is that obviously the program that I'm using, which is fritzing, doesn't have block detectors in, but these are, if you like, where your block detector inputs would come in. Most block detectors, you're not going to need the pull down resistor. It's going to send either a high or a low. And the other bit, of course, is I've got these connected to directly to the Mega. The same with my buttons. You can do that, but obviously you're limited to the number of pins on the Mega, and with the ESP32 there will be even less. So you may finish up connecting your block detectors to some kind of port expander or shift register, but for the demo today I'm going to be just connecting them straight to the board. If you want information on how to set it up with other items, just contact me off the Digital Town site or just put a comment below the video. When it comes to the servo driver boards, I've just put the example of one LED in, and then I've just listed the colors that I've got the different LEDs set at for each of these positions. So you've got signal 6, which is 4 aspect, 7, 8, and 9 are 4 aspect, 5 and 3 are 2 aspect, 10 is 4 aspect, and 1 and 2 are 2 aspects. So the wiring, although it looks crazy on the breadboard, is fairly simple. It's all using an I2C connection for the 2 servo driver boards and the backpack display. One thing, of course, if you check the previous video, it will show you how to make sure that you've got different addresses for the servo driver boards. You need to solder across these tabs. So going to the demo sketch, as we come down here, we've got, if you like, the bits that are required for the interlock system. Then I've started to add the other items. So I'm using the liquid crystal display. So I've included the I2C liquid crystal library. I'm using PWM's PCA 9685 servo driver boards. So my addresses were 40 and 70. Those are the different tabs I've got soldered across. You'll notice obviously they have different names depending on the address. I've then set up my different pins. So I've got my block pins. So coming back to the circuit diagram, these are mimicking block detectors, and they are on this set of pins here. Let's just move that out of the way. So those are on pins 44 to 52. And then the buttons that I have, if we look, I've got 6 buttons. 1 is being used for the mode. 5, 3, 2, and 1 are signals, and 4 is the turnout or point. Let's get the code back up. So you can see here that I have got my main buttons connected to pins 22 to 28, but my mode pin I connected to pin 10. I'm using current millis for timing with a debounce, and I've set that debounce to 350 milliseconds. And then I've also got the buzzer pin for the speaker, which I've got on pin 12. Now, obviously, this code is set up to the system that I've built. If you're using different input methods, you're going to have to write your equivalent code, but this will give you a good starter on how to do it. So coming down to my main loop, obviously, I've got all of the interlocking stuff, and then I've got my screen code. So I'm starting the screen, turning on the backlight, setting the cursor, sending some text, setting the cursor, sending some text. So that checked the screen was working. I'm then starting the two PCA 9685 boards and setting their frequencies. I'm attaching my servo pin. And then I am working through the PCA 9685 boards, both of them, and I'm going through the whole lot, and I'm turning all the LEDs on, and then I'm turning them all off. That's just a good way for me of making sure that everything is working correctly. You'll notice I move the servo, then I have a delay. You can have a delay in the setup, won't cause you a problem. Put it in the main loop, big trouble. Then I'm moving the servo back to its start position. So this code is basically making sure that everything that I attach to the board works. On a layout, if you were setting this up for a real layout, you would test that it works, but then you would comment out this section, because you certainly wouldn't want a turnout to move in two directions when you started your layout, because you could have a loco that was parked over that turnout. Not going to end well. I've then gone through my array of block pins and the array of button pins, and I'm setting the pin modes. Now, if you're not sure about arrays, if you go onto the Digital Town site in the beginners course, Arduino course, there is all sorts of information about the basics of Arduino programming. Coming down to the main loop, we've got our my Signalbox.run interlock, so that just stays there as normal. I've then got a variable current millis that updates to the latest time in milliseconds. That's for debouncing my own code. And then I've created a function process buttons. So my main loop looks quite clear. We come down to process buttons, and this is just going to check through the debouncing again. You can go and have a look on the website, Digital Town site, on using millis for timing. There is actually a link from the bottom of the page to do with the interlock system. If we just bring that up, if you scroll right down to the bottom of the page, there is a whole set of videos on using different components and how to get them to work. So coming down to my process buttons, first of all, it's going to go through all my block detectors, and it's checking to see if the status of the block detector has changed. If it has changed, then it calls this function block pin process, and block pin process here will send an instruction to my Signalbox to check the status of these items against, if you like, the interlock rules. Now you'll notice, even though this is a multi-aspect signal, there are only two values that you send across. You either send signal stop, which is a 0, or signal go, which is a 1. The monitor system will then work out what aspects should be displayed based on these other signals around it. So I'm just working then down through all the other items. Obviously, this is the position in the array. If you want more details on this, I can do some other videos later on, but this video is already getting quite long enough. The other item that I'm then checking is once I've done my blocks, which is this bit of code here, I'm then working through the array of buttons. And again, this time I go to a function called button pin process. That function is down the bottom. And again, this just works out if it's a 0, that was to do with signal 1. And it's just sending the interlock instruction across. Finally, down at this last button, I've got one that's actually sending the mode state, so I can swap the mode over. Now, the reason for not going into full details of this code is depending on the type of buttons, block detection system, whatever, you will set up your code your own way. The important thing is to see, if you like, the idea of what happens, and the only thing that needs to be sent across then is this function checking your interlock value for that particular item. The system will then work out the rest of it, and your output, if there is an output to come out of it, will come out in your check results, and your, here we go, what's the name of this function at the top? Keep going. It's going to be in the int update layout. So that's what your inputs are. Your check the rules, this check interlocks, and your outputs come out in the int update layout, and that function below. Got so many items in this one. The int check results, which you would use for a display if you want to. So I hope that's been useful. All the information is available on the Digital Town website. It's been a bit of a long video, so I'm going to finish it here, and we will, if there's any questions, just send them to me or put a comment below the video and I'll deal with them in a separate video. So I hope that's been useful to you and shown you just how much you can do with an Arduino or an ESP32 when it comes to signaling simulation on your layout. I'm going to be adding some signals to my layout over the coming months, just because I want to try some of this out for myself. My layout, because it's narrow gauge, doesn't tend to have many signals. If you've got any questions or you want something clarified, please just email me or put a comment below the video, and I can either respond by email or even do separate videos. Again, depending on how your inputs are set up, you will have slightly different methods, and I can cover those if you want as well. So thanks for watching, and if you've got any questions or you find any bugs or you've got any ideas of features you would like added, just let me know and I'll see what I can do. Thanks for watching, and I'll see you in the next video. Bye for now.